Hello and welcome back. We will continue with Chapter 8, which is all about hypothesis testing by looking at Section 2. Section 2 will be on hypothesis testing involving proportions. Section 3 is going to be about means, and Section 4 will be about standard deviations. So we'll focus entirely on proportions in this video. And I think it's easiest to go through just examples and see all the steps again. We have that in a study, 29.2% of 19,139 participants said that they have sleepwalked. So the question is, can we claim that fewer than 30% of people, of all people, sleepwalk? So here we have some information about a sample, and we want to make a claim about the entire population. So this will be a hypothesis test. So our claim, we claim be less than 30% of people sleepwalk. Okay, so it's basically as simple as stating what they ask us in the question, but we also want to make this into a symbolic claim. So we'll let P be the percentage, or I should use more technical language, would be the proportion of sleepwalkers. And this is in the entire population. So our claim is that P is less than 0.3. So here is our claim, is that the proportion of people that sleepwalk is less than 0.3. Now, in order to really test this, what we need to establish is a null hypothesis and an alternative hypothesis. The null hypothesis, we normally write H0 or H0, and H1 is the alternative hypothesis, although you will see HA as well. The null hypothesis is always setting the proportion that we're testing equal to the value that we're looking at. So the null hypothesis here is going to be P is in fact equal to 0.3, and we will either reject this or fail to reject this. And if we reject this, the alternative will be that P is in fact less than 0.3. So we have the null hypothesis and the alternative hypothesis. The significance level is just stated in the question. So alpha here is going to be 0.05. This is our significance level. And if you remember from last time, this is going to be the probability that we get a type 1 error. As in, if we reject H0, but it is in fact true, this is called a type 1 error. And there's a 5% chance, and we want to minimize the chance that this happens. So we will only reject this if the probability that this were to occur is less than 5%. So now becomes so the next step is determining the test statistic, which is going to be the most calculation intense part of this, but it's still not bad. Proportions are normally distributed, as in the sample proportions are always normally distributed, and because we have a normal distribution, our test statistic is going to be Z, and this is and this will be equal to our sample proportion minus our population proportion divided by our standard deviation, sample standard deviation, which is going to be PQ over N. So this is again something that you will just be able to look up, remembering which test statistic goes with which parameter that we're looking at. In this case, because we are looking at proportions, this is the test statistic that we want. So we should recall what each of these are. So p hat is going to be the proportion in our sample. And our sample, we had 29.2% people said that they sleepwalk. So p hat is going to be 0.292. P, on the other hand, is going to be our population parameter. And although we don't know what it is, this is what we are testing. So we are testing that p is going to be 0.3. Q, on the other hand, if p is the probability that someone is a sleepwalker, Q is the probability that someone is not a sleepwalker, and this is going to be 0.7. Notice how p and q should add up to 1. Lastly, N is the number of people in our sample, which this was a pretty big sample, 19,100 and I think I wrote this down wrong. I think it's meant to be 36. I'm following an example from the book. So this is going to be 19,136. So we plug everything in, we get 0.292 minus 0.3 divided by the square root of 0.3 times 0.7 all over 19,136. And this turns out to be negative 2.415, or if after I've rounded to 3 places. So here's our test statistic. And the goal is to see whether or not this test statistic is unusual. If it is too unusual, that means that we made a wrong assumption. And the assumption that we're making is right here. We're assuming that the population has 30% sleepwalkers in it. This is our assumption. If this is too unusual, we get to reject our assumption. We get to reject our null hypothesis. So, how do we determine how unusual this is? Well, because we're looking at z values, all of our values are coming from a normal distribution. This is normalized, so this is coming from the standard normal distribution, where we have the mean of 0. Negative 2.45 will be over here. 415. And to see how unusual something is, because we are wondering about whether or not the parameter is less than 0.3, this is going to be a left-tailed test, meaning we just need to find the area under this curve right here. And it's going to be to the left because we are worried about proportions that are smaller than 0.3. So we come back to, for instance, StatCrunch. We can go to Stat, we can go to Calculators, and go to our normal distribution. And from here, we want to see the area to the left of negative 2.415, and we get 0.00 if I round to 8. So our p-value, oops, don't want it to be red, our p-value is going to be 0.008. So the area over here is going to be 0.008, which is where I get this value from. Next, we want to see, do we reject this value or not? And since the p-value, which is 0.008, since this is less than our significance level, so p-value is less than alpha, we reject. So, what have we rejected? We have rejected our null hypothesis. We have rejected that that the proportion of sleepwalkers is equal to 30%. That means that our claim that p is less than 30% is being supported by our test. So our conclusion is that there is sufficient evidence to support the claim that the proportion of sleepwalkers, I'm going to abbreviate here, I'll run out of room, of sleepwalkers is less than 30%. And that's our conclusion. We can reject the null hypothesis, which says that the proportion of sleepwalkers is equal to 30%, which means that we can support the claim that the proportion of sleepwalkers is less than 30%. One final remark here. There are restrictions on when we can do this. And this is both quite important, yet at the same time, most of the time this is satisfied anyway. So in order to apply everything that I've just said, n times p, and this should be n times p hat, and n times q hat, have to be greater than 5. N times p hat, the number of people in, or the number of things in the sample, times the proportion of successes in the sample. This is just how many successes are in the sample. So there has to be at least 5 successes and at least 5 failures, as in at least 5 people needed to say that they were sleepwalkers, and at least 5 people needed to say that they were not sleepwalkers. So before we did any of this, we should check what is n times p hat, for instance. And this, so if I take p hat, which is 0.292, times n here, we in fact get 5,587.7, but we can't have 0.7 people say that they were a sleepwalker. So we need to round to the nearest whole number. And this is certainly bigger than 5. So there's no need to worry here. The number of failures would be the other half of this. So if 5,500 people said that they were sleepwalkers, the other 14,000 people said that they weren't, and that's also certainly bigger than 5. So this is important to check. We need to check that n times p hat is bigger than 5 and n times q hat is bigger than 5. Most of the time this is satisfied.